Hello everyone. Today I will give introduce a work about G memory tracing hierarchical memory for multi-agent systems, which is newly accepted in Europe's 2025. In this background, we can firstly to see the graph for existing single memory and multi-agent memory. The single agent memory will maintain limited performance compared to the multi-agent system. Sorry, the single language model will underperform compared to multi-agent system, but the development trending of single agent memory is um, more trending because they have developed cross-trial memory, broaden the application domains, and enhance the management on more sophisticated abstraction and summarization. However, for multi-agent systems, it suffers from the undeveloped memory architecture because for the memory scheme, it mainly consists of inside trial memory and cross trial memory, which depends on which depends on whether we store the memory of one trial or multiple trial. And in this case, for multi-agent system, they mainly use the inside trail, but the existing approach with cross-trial memory is merely use the compressed final outcomes. And because of this, this is over simplistic and degrade the inter-agent collaboration trajectory and which lack of the impressiveness because the cross-trial and agent-specific customization is overlooked, and moreover, it is infeasible to leverage single agent memory directly because for a multi-agent system, it has more longer task solving records, which is hard to encode directly. Based on the authors in this work aims to memorize lengthy interaction histories, but provide more concise instructions. And they propose dream memory. In this talk, I will share you with three experts for architecture retrieval and updating. And for the architecture, Gene memory utilizes a hierarchical agentic memory system for multi-agent system, which concludes three hierarchical graphs: inside graph, query graph, which link the inside graph and interaction graph in the middle, and the interaction graphs. And for retrieval, the memory knowledge from the G memory, it designs a bidirectional memory transversal to based on the upward insight, they can leverage cross-trial knowledge, and based on the downward fine-grained condensed interaction trajectory, they can compactly encode the prior agent collaborations. And based on the G memory queries, they can update the new collaborative trajectory to realize a several evolution along with the evolution of a multi-agent system. And let us first to define the multi-agent system formulation. Multi-agent system can be treated as a direct graph where for each node they can contain the initialization of a language model and its role and memory state of itself and some external plugin for the tool using. And the edges are the topological connection between the defined by the agent collaboration. And given a user query, the multi-agent system will conduct T epochs of communication. For each epoch, they will have a topological ordering to define which agent who is the predecessors of this agent, and for agent I, it outputs based on the system instruction query and the response of its labels, and to generate its customized response. And given all the responses from all the agents, they will have an aggregation such as majority voting and hierarchical summation, or directly choose the final agent outputs and to summarize a solution in the end. And now when study the gene memory architecture, it consists of 3 graphs. The first graph is we will use is quite so directly is interaction graph, which is directly the agent with its context textual information, which will record it as loads, and the dynamic interaction between agents are constructed the interaction graph, the edge of interaction graphs, and based on it, we can utilize the semantic similarity to construct the query graph. It mainly stores the query and its status of this execution, and its corresponding interaction graph as the nodes for the query graph. And based on the semantic similarity, we build the edge of the query graph. And the insight graph is a high-level insights summarized from the historical interactions. It mainly has the high-level contents for the summarization of the existing execution, and for each insight, it has a supporting queries consists of the queries which is related to this high-level content, and the edge of the inside graph can be constructed by a hyperlink, which is the relation between insights and the corresponding queries. And once we build the gene memory architecture, we can utilize in the multi-agent systems, such as given the new query, we firstly to conduct the similarity-based retrieval to find the related queries, and based on it, we have conduct the bidirectional transversal to seek the related insights and interactions. And based on the knowledge they will utilized in the real task of the multi-agent systems, and given the feedback from environment, we can update the gene memory architectures. And then we will go deep details of how to do the workflows. Firstly is coarse grained memory retrieval. This is quite simple, which is mostly utilized in existing multi-agent systems, such as we can compute the semantic embedding for new queries, and its highly related existing queries in the query graph, and finding the top k mostly related one as the query set. But and we can use multi-hop expansion to enlarge the query subset. But however, this approach has limitations. Firstly, it will memorize the lengthy context, and it cannot assign specialized memory tailored to the task functions. In order to mitigate it, they propose the bidirectional memory, which will utilize the high-level insight and fine-grained interactions simultaneously. To upward transversal, they will seek the subgraph of insights based on the query subgraph. The thing is do that by a projection, which is to seek the insight whose supporting set has the intersection with the existing query subgraph, and based on it, they can collect the insights as the insight subgraph. And for downward transversal, they will find the interactions based on the existing queries, such as firstly to collect the top and relevant queries, and given the queries, they will specify the interactions correspond to the highly relevant queries and to get the final interaction, because the fine-grained interactions are overwhelming, so we will have a specification. And once we have obtained the inside subgraph and the interaction subgraphs, we can utilize them with a specialized memory based on the role the agent has and the query corresponding to the task, and to get the customized memory for agent. And in the specification, they use the prompts as below. Mostly to they will have instruction to highlight to identify the critical steps. And for query the relevance, they will use the to compare to descriptions. And given the bi-level retrieval, we have obtained the retrieved memory, which will be used in the multi-agent system. And then after the execution, we will have the status of whether success or failed in this memory. And based on this knowledge, knowledge trajectory, we have an update for the hierarchical memory. For the interaction memory level graph, we can directly construct the interaction based on the historical interaction trajectory and the query. And for query level subgraph, they will collect both the most relevant queries and as well as the supporting sets from the insight. And based on this, they will construct the edges for the new queries, and we can update the query set with both the query node and the query edges. And then for updating the insight level, the first trial is to summarizing the experience by linkage or summarization. And in this case, we directly choose the hyperlink of the historically the retrieved insight subgraph and the new insight condensed by this episode of interactions together. And based on the query, we construct the hyperlinks. And once we have the hyperlinks and the loads, we can update the insight graph. And meanwhile, we will also updating the supporting query set for the new insight graph. And firstly, we will remove the utilize the insights, and because we will modify it to introduce the introduce some query knowledge for the modified insights and as well the new insights. And based on it, we will update the whole insight graph. And to construct the insight graph, they will utilize summarization function, mainly focus on the highlighting or itemization or merging. And one more thing, they also provide a customizing memory, such as highlighting the personalization in the highlights. And in their experiments, they mainly studied three problems. The first one is, how does gene memory perform compared to existing single or multi-agent memory architectures? And the second one is, does gene memory incur excessive resource overhead? And the last one is the sensitivity studies. And to conduct the experiments, they mainly utilize the data sets from three experts. For knowledge reasoning, they utilize hot pot QA and fever. And for embodied actions, they use AF word and SI word. And AF word has multiple tasks. And for the game, they use PDDL. And for design comparing the baseline, they both utilize the single agent memory and the multi-agent system memories. And they choose three multi-agent systems as the backbone: Autogen, Dylan, and Magnet. And they use three language model as the base initialization for Queen 2.57b and Queen 2.14b and GPO 40 mini. And to study the gene memory performance, they provide the results, which is evidently that gene memory is competitive on three models. Sorry, I didn't list the last two models. And gene memory surpasses the best performance on both the single and multi-agent memory baselines. And for multi-agent systems, they demand the specialized memory designs. And Voyager and the memory bank degrade on DDL due to not providing agent-specific memory support. And ChatDevM's narrow memory scope provides limited utilities, making them underperformance on the embodied action environment. And this core highlights that both all the role specific memory queues, abstracted high-level insights, and trajectory conversation work to the performance of multi-agent memory architecture. And in the evaluation, trade-off between the token cost and performance, G memory have achieved the highest performance improvement over the long memory setting, and and um, and they have but they just modestly increase the token consumption. And compared to the Meta GPTM, they have request additional 2.5 billion token for a mere 4.4% of gains. And to the sensitivity study, they consider the multi-hop expansion and top K selection and the ablation studies. From the figure A, we can see that the benefits of expanding the query subgraph is limited because just one hop obtained the best performance. And for the sensitivity of top parameter K, we can find that slightly increase the top K will have benefits, but continual increase will reduce the relevance of queries and degrade the performance. And for the ablation study, it can evidently observe that both utilizing both the interaction and the insights, we can achieve the best performance. And there also have some case studies for once we have a query query and the multi-agent system, how can we retrieve the high-level insights and fine-grained interaction trajectory? And based on it, for two data sets and for three data sets and three multi-agent systems, the combination we can find that both the high-level insights is corresponding to the fine-grained trajectory. They have a it seems like that high-level insights provide the rules for executing this task, and the fine-grained trajectory providing the detailed executable action sequences to as a reference for the similar query or task. And in the visualization, they also visualize the inside graph, and based on it, we can find that dense intra-category connections among insights derived from the similar tasks, and there has an emergence of meaningful inter-category links reflecting the transferable patterns across task domains. And for the query graph visualization, the directed edge between the two query nodes indicates that the historical trajectory of one query offers useful guidance for the execution of another. And based on it, we can find that the groups of semantic similar queries from densely connected subgraphs and sparser intercluster edges capture the cross-task inspirations, and both of these findings verify the effectively organized and relate the collaborative experience through the structured memory can boost the learning and enhance the performance of multi-agent systems. That's all. Thank you.